Well, the connection with HPC is that we are a user of high-performance computing systems, and nowadays, in the research of computer science, almost everyone is using GPUs. So every student in our department usually have access to 4 to 5 sort of GPUs in their research. Okay, so in particular, I'm going to talk about computer vision for autonomous driving. So first of all, let's start with what is computer vision. Okay, so computer vision is a research field inside the computer science, has to do with processing of visual data. Okay, so in general, for computer vision systems, the input would be visual content such as images or videos or 3D point clouds. Okay, the output will be some knowledge from the image you wish to obtain, such as given this kind of image, you want to be able to answer questions such as what is the scene, right? How many cars in the scene, right? What are the distance for each of car to my cameras, and so on and so forth. So the way to answer those questions is by designing algorithms, right? Algorithm can run on GPU, run on servers, which can essentially process the data and sort of produce answers and to these questions. So computer vision is a field that has been in our community for many, many years, and vision has many applications because essentially computer vision tries to solve the question that we wish computer have the same intelligence when they look at the visual content. Okay? So vision has been applied for problems such as image classification, and in medical image analysis, you see vision algorithm is helping doctors to essentially look at pictures, look at the scans, and to detect any potential problems. And vision also used to 3D reconstruction. You can have a UAV fly through the building and to do a 3D reconstruction of the buildings, right? And in sports, for example, World Cup, you see a lot of visualization, which are also come from computer vision as well. And so there's 3D reality and as well as Amazon Go, right? And Amazon Go trying to build a store where no people is looking. Everything is through the sort of vision systems. And finally, autonomous driving is certainly one of the biggest applications right now for computer vision. So when we talk about autonomous driving, we saw there's 5 different levels of autonomous driving systems from level 1 until level 5. Among those, we typically say that there's a sensing system essentially trying to capture the surrounding environment, either using camera or LiDAR or other sensors. And there's a perception, essentially trying to process in the data and to try to understand what's going on. And with that, we have planning. We can plan the path of the driving of the car. And finally, we put the planning into action, which is control, right? So this 4 modules will essentially come in an iteration and going over and over as time flies by. So among these 4 components, the component we have most impact for computer vision is actually the perception. So that's the area I'm going to talk about today. So in perception, we see there's 2 different kinds of perception. One is called outside perception, meaning the sensor is looking outside of the car when I'm driving. Right? So in this case, the major task would be trying to detect and recognize, as well as keep tracking of the moving object, especially moving object in the surrounding environment. That's the main objective, right? So in particular, I'm going to talk about 4 different topics in our lab in the research part, from low-level vision, understanding the low-level pixels, to object detection, and to the object forecasting to predict into the future, as well as I'm showing you one application in terms of trailers. Okay. And the second kind of perception is called inside perception, right? So the camera and sensor can also look into the car, inside the car, and to see what happened to the driver, what are the things that the passenger is doing. So this is quite useful to especially monitor the status of the driving, because we think that in this current period of moving to the level 5 autonomous driving, there's going to be a long period of time in the driver's seat. There's still going to be someone is looking at the situation, make sure there's no dangerous thing happening. Okay, let's start with the outside perception. Talk about low-level vision. So what low-level vision trying to do is that oftentimes you assume there's a very ideal imaging conditions, right? In the daytime, in the very sunshine lighting conditions. But what happens if you have unideal situations, such as driving in the dark, or in the low resolution condition, or there's a snowing, or there's raining, and whenever that happens, sensing becomes not so reliable, right? You are getting image content that's pretty bad qualities. In those cases, how do you want to make sure the vision system is still robust? So this will need a low-level vision system to do the processing. So let's look at one example. It's called super resolution. So over here, you see one example where the left-hand side of the green line is low-quality images, and right side of the green line is a super resolved by 4 times super resolution. Meaning, if the input image is 100 by 100, you generate an image that's 400 by 400. Okay? So with that, you can see that the low-level image quality become better, and you can see more detailed information on the images. Okay? So oftentimes when I talk to people from GM or Ford, they mention to me that in the RGB camera on the cars, they don't wish to install very high quality cameras because in those cases, the dynamic range of the car will be substantially reduced. So therefore, it's not going to be well to handle extreme brighter as well as dark situations. So therefore, there's a need to do super resolution on the RGB cameras. So for this problem, our contribution is that, so you can see that this is a comparison for multiple methods right now in the research community, which perform the best, where the vertical axis is PSNR, indicator how accurate you can do image super resolution, where the horizontal axis is the number of parameters in your model. Right? In general, we say that the number of parameters, the more processing time you have to do the super resolution. So you can see that compared to other people, other approach, our method, which is the 2 red dots, can have higher PSNR, but especially with a lower number of parameters, which is very important to run system very efficiently in the real-time systems. So this is one example showing you some of the results. So you can see that the first column is the ground truth. The second column is the input to our system. And the remaining 4 columns are the different methods. And the last one is what our system is able to generate. You can see that even with very low quality images, the super resolution algorithm can substantially enhance the resolution of the image. Similarly, this kind of algorithm can also be applied for image denoising. Right? So what happens, the input image, which is the second column, has lots of noise, salt and pepper noise. Right? So this kind of noise can also be going through the deep learning algorithms, eventually generate a pretty high quality image showing on the right-hand side. Yeah? Now, what about in the dark? Right? We know that RGB camera is not that great in the dark environment. So what you see here is that the top row is showing the input image to our systems, which is capture surrounding content in the dark environment, 12 p.m. in the night. But by taking these kind of systems, this kind of image into the systems, actually the algorithm can generate what's shown in the middle. So that's our estimation in the middle one. Right? Essentially, it's trying to moving the histogram of image from a very narrow band, which is extremely dark, to a full 256 dynamic range. In the meantime, trying to suppress the noise. Because when the camera is capture image in the night, there's a lot of noise, sensor noise. So that noise has to be reduced. Therefore, what you see in the middle one is our system output. What you see in the bottom is the ground truth images. Okay. So with that, let's move to the second part, which is object detection. So what you see right now is MSU campus. Okay. So we are running our system basically on the video sequence we capture when we are driving in the campus. So every yellow box is a detected person, pedestrians. Right. There's also a number on the top left corner of each box that indicate what's the distance, how many meters from the person to my camera. Okay? So this system can run about 10 to 15 frames per second on a GPU. So it's pretty efficient, and we can detect any person that's within 40 to 50 meters away from the camera. So our system has been detected with pretty interesting design. So this is a kind of the network architecture we did on our systems. So one of the big things compared to previous work is that we have this so-called the segmentation loss, meaning that not only we're trying to detect object, but we're also trying to segment object from the background. So with the segmentation loss, we find that the detection performance can be substantially improved. So this is one visual example showing that compare our method with the Facebook method called FastRCN. So this is so-called the feature map. Basically, the amount of yellowness indicate whether I have people present in the video sequences. You can see that in the baseline method, there's a lot of unnecessary yellowness indicate the potential false alarms. But in comparison, in our method, the yellowness is much more focused on pedestrian, focused on people. Therefore, we have a higher detection rate. Okay? Well, in the meantime, we have a lower false alarm. So this is the, let me see. Okay, so this is a quantitative comparison between many different methods in the research as well as industry on a benchmark database called Caltech. So in computer vision, every problem we study, there's a benchmark database. So everyone, working on the same database so that we can compare which algorithm eventually works the best, right? So in this database, as you can see from 2005, 2008, in the past 10 years, many different universities have been working on this database. So right now, MSU, our method, which is the green one, has the lowest missing rate. Missing rate means that the lower the better. You don't miss any person, right? In the meantime, we have a lower false positive rate per images. So you don't want to have false positive as well, okay? So the second problem for the detection is actually semantic segmentation. So over here you see that the top one is still the detection, object detection, but the bottom one is so-called the semantic segmentation, where I'm trying to classify every single pixel into one of the 20 different categories on the right-hand side, right? Including sky, vegetation, poles, traffic light, and so on and so forth. So this is a very comprehensive understanding about the surrounding environment. So with that, you almost understand everything you see from the cameras, from RGB cameras, right? From those images, you can see that the segmentation quality is pretty high. The leg, the hand movement can also be captured because of segmentation, okay? So one of the recent things we did in school is that the MSU has this traffic monitoring systems. So on the intersection of many streets within the campus, we have surveillance camera installed on those streets. So actually, those cameras can be real-time stream videos to our lab, where my student can do the processing. So in this case, we're actually taking the MSU campus cameras real-time stream into the lab, and then our system will be running on those video sequences. As you can see that in this over here, we do multiple object detection, including car, riders, buses, and peoples, right? Everyone is being detected and tracked. In the meantime, in the bottom, you can see that we can estimate the traffic flow of people as well as vehicles. So we have the person in terms of eastbound, westbound, southbound, northbound. So these are the detection, tracking, counting for every single person, right? So the system can run about 6 to 10 frames per second on a single GPU, okay? This was a little bit old result. So right now the speed can be even faster. Yeah, so this could be fairly useful for traffic monitoring. Okay, so far all the system you have been seeing is running on GPU, running on HPC, right? But another trend in the vision community is that not only I want to running my system on GPU, I also wish to run on the edge. Meaning what happens, I have low-cost devices, low-cost chips. Can I still run my deep learning systems? So in this case, we're showing that, yes, you can actually do that. We're taking the pedestrian detection as one example. So in particular, we're running on a chip called ARM-i3, which is 800 megahertz chip. This chip is as cheap as $3, less than $3 chip, right? But even on this chip, our system right now on pedestrian detection, we can run about 8 frames per second on these kind of chips. Because we have substantially reduced the network size to make it really efficient, to have less multiplication, summation, and subtractions. So therefore, eventually, the model can be run really, really fast. So you can imagine if I have a small camera and a little chip with only $3 to $10, you can install everywhere as you wish. Yeah. Okay, so the next question we are showing you is that what about, I can analyze what I see right now. What about in the future? Can I predict the futures, right? So in this case, we're trying to say that on the top is the current video frame I'm seeing from the camera on the car. From that video and the previous video sequence, can I predict in the future, in the next half second or 1 second, how the different things will be moving around on the street, right? So therefore, we are using the current video frame and previous one to estimate the future segmentation mask. And we overlay the estimated segmentation mask on the future frames. That's what you see in the second row. Okay? So the time difference, the future you are predicting is about 0.15 seconds in front of you, basically, right? So the fact that if you look at the second row carefully, the fact that the color actually overlay very well with the actual object means the estimation is pretty precise. Yeah? So if the car is driving at 30 miles per hour, within 0.15 seconds, actually the car can move about 2 meters. Basically, we are saying that if my car moving in 2 meters, how the different things will be changing. You can see that this can be very useful for the sort of path planning.
So are you seeing just 2D images? Are you trying to do image plus infrared? What happens if I have pictures of people? Are you identifying the image as a person? Or are you identifying the image as a person, or is it detecting that that's just a 2D picture?
We are detecting them as different objects. So because by looking at the color of the segmentation, you know what you are seeing, whether it's people or cars or
and the
trees.
the color's coming from image plus infrared, or it's synthesizing
only RGB, only RGB. The input to our system is only RGB video sequences.
All right, so if I pop up a picture of a person, it's going to think it's a person.
We have a system later does that called spoof detection. We can tell what's the difference between a real person versus a picture of a person, for example. Yeah. Okay, so this is more example of the prediction, and I can also show you a video sequence. So again, on the top is the current video sequence. That's the input to our systems. In the bottom is the predicting into the future and overlay on the future frames, right? You can see that most of the time the prediction is pretty well aligned with the actual object content. And when the car is bouncing because of the surface of the road, the estimation is also bouncing around. So it's kind of together with the actual content. Yeah. Okay. So for outside perception, the last work I'm going to show you is our collaborative project with GM. So the goal is very simple, right? Most of you probably have experience, deal with trailers. When you're trying to hook up with your car with a trailer, it's not very easy. You have to kind of watch back as you're driving back, right? So GM has a hope that why don't we have a one-button car backup system for hooking up with a trailer? You push a button on the car, it will go back by himself without actually driving. When the car stops, all you have to do is lower the trailer tongue so that it's on top of the hitch, right? That's the best situation. So to do that, you can see that there's a control system for the car, automatic control system for the car, but there's also a vision system is necessary to detect and track the trailer tongue automatically without any human assistance. So that's essentially what we did, together with GM. So here you see how the system works. So basically, starting from further away distance, about anywhere from 5 to 10 meters, you park your car, and then when you start to go back, our system can detect and track the trailer tongue automatically in the 3D sense, meaning that we're estimating this location in the XYZ coordinate, not just in 2D XY pixel coordinate, because the car control needs a 3D coordinate to tell him where he should be moving to in the 3D space. Yeah? And the challenge, of course, here is that you got to make your system work in any kind of trailer, any kind of weather condition, any kind of lighting condition. That's extremely hard. Okay? So therefore, we actually went through almost all the RV parks within the state of Michigan, captured thousands of videos, and label them, and train our system, and test our system to see how well it works. So over here, you can see that the yellow one is manual label ground truth, and the red one is our system output. Eventually, the CTQ here is that when the car stops, the estimated distance and the true distance need to be less than 2.5 centimeter, because that's the radius of the ball. If you're more than that, it's not that useful. Okay? So yeah, we deliver a system to GM. You know, hopefully in the next few years, you see this kind of feature will be offered in their latest cars. Okay, so now let's move to the inside perceptions. Okay, so for inside perceptions, our group has done a lot of work on faces because that's my PhD thesis topic when I was in CMU, and I'm still working on that. So one of the topics we work on is called face alignment. Basically, you want to understand the structure of human faces, right? Especially when the face is in movement. So over here, you see that on the top, we show you that when the input face in different poses, we can always fit the 3D model onto the faces. That's a second row. With the 3D model fitting, you get the facial landmark points, meaning there are 50 points on the face. You want to keep track of them, right? So the location of those faces indicate what's the pose orientation of the face as well as what's the expression of the face, right? We can do this very reliably. So if you take one step further, not only you can do the face alignment estimating point, but you can even estimate the surface, right? Here we're showing you that if I type his name, William Shawn, his name into the Google image search, I can get 50, 100 images of him from Google Image, right? From those 2D images, I can actually reconstruct 3D model of that person. So that's what you show in the second row, right? So one application would be that over time, you can get a lot of 2D images of a driver, so you can easily build a 3D surface model for any drivers with this type of method. And the reconstruction quality of the 3D surface model is fairly precise. So there's wrinkle level detail also being reconstructed. Yeah, it's actually typically it's much more accurate compared to what 3D scan can give you, unless you are using a few $1,000 very high quality 3D scans. And we do this for male and female. Female typically cause more problem because of different hairstyles. As you can see, the hair is being reconstructed as part of the 3D surface as well. Okay. Now, the previous work of 3D reconstruction was from multiple images. But our latest work in this year, we also can do this kind of 3D reconstruction for single video sequences. As you can see, for single video sequence, we can take every single frame, reconstruct the shape, 3D shape, as well as his mouth and face movement. We can swap him with other faces if we want to. So we can synthesize another person in the same way of his talking, basically. Yeah. So one of the interesting projects we did last year was that in surveillance applications, oftentimes you see side view images, right? Now, if you want to do face recognition, you need to match the side view image with the frontal view gallery ID photos. So the cross view matching is typically a problem. So we're asking ourselves, if you see the side view images, can you virtually rotate his face into front view, get a front view picture of that person? Is this possible? Well, yes, we show you actually it's possible. So the top row is input to our system, any single image. The second row is our system output, is a synthetic photo of that person in the front view. So you can see that if you look at every single column, the identity is being well preserved. It looks like to be the same person. And if you compare with the ground truth, indeed, it looks like to be the same person as well. And also the image quality is pretty high. The synthesized image quality is fairly high. And we can also feed those synthetic images into the recognition. We do see that the facial recognition system is being improved because of this ability to synthesize front view images. Okay? Okay, so finally I'll show you a system that John was just asking, right? What happens if you see a face? It's not real face. It's actually some picture of people's face, right? This, in our case, is called presentation attack detection, called PAD systems. So in this case, we are actually developed a PAD systems that the system can run on a cell phone. So the cell phone you see is running our system right now, okay? And you see the box, the color of the box, the green means it's a real face, the red means it's a spoofed, it's an attack. It could be a paper attack. It could be a cell phone attack. It could also can be a 3D mask attack. Someone make a 3D mask for you and trying to tackle the systems. Yeah, this is also one of the attack as well. So this project was sponsored by RRPA. We have been working on this for a year and a half. Right now we are into the phase 2 of the project. The ultimate goal is that what happens if someone have a picture of a person on the street, and the autonomous driving car sees that picture and trying to think that's a real person and stops, but actually it's not. So you need to be able to tell whether it's a real person or actually a picture of some person. Yeah, so that's one application of that. Okay, so that's all I have. I'd like to thank my students who are working on those projects, as well as sponsors who have been sponsoring various projects. Thanks.
Questions?
So how much are you seeing compute being at the point of detection in the vehicle and the sensor itself, vice throwing it back into the cloud for an HPC task? And where do you see HPC playing in this environment?
Very good question. For autonomous driving, I don't see any possibility of using HPC. The reason is that time delay is so critical. You cannot putting those tasks into cloud to do the processing because the time delay cannot be controlled. All the computation have to be done on the car, in the car, immediately. So that's why, car company is not willing to pay a big cash to NVIDIA to buy all the GPU cards put into the car. So they want to do everything computing on the edge. So how to make the algorithm to be more efficient using low-cost chips so that overall the autonomous driving car will be cheaper. I think that's a big thing. Otherwise, if you put 5K, 10K cards, the car price will go up very fast.
Right. Yeah. But do you see an HPC play in this ecosystem?
Of course, they're not in the inference stage, but they are in the training stage. In the training stage, when you want to train a model, you will use HPC all the time, every single time. But during the testing, you probably want to use less HPC because of cost. If I can afford in high-end car, I can put 10 GPU cards. Of course, that's preferred. That's best for eventually the algorithm performance. But for the cost reasons, I think people will prefer to use less GPUs during the inference time.
What model GPUs and what programming languages do you use?
We use Titan 1080p. So it's typically a 1K price tag for each card. So the latest one is 2080 Ti, I believe. It's 1.3K, but it's not on the market yet. It's coming out pretty soon. Yeah.
Programming language?
We Python, C, and other major languages, Python and C. Yeah.
So just a quick question, follow up on that. I mean, how could you characterize the computational power that's in your inferencing engine, just to kind of put it in terms we could understand?
Okay, sure. So the most direct way of quantifying computation time is using how many frames per second, right? So on the certain platform, that's how you compare. But people also trying to do more detailed analysis in terms of how much multiplication you are doing in your inference stage, because the number of multiplication typically is linear to eventually the speed. So that's another way to do it. So that's why you want to design your network so that it has as less multiplication as possible.
But in terms of the examples you've shown here,
yeah.
How would you characterize their complexity in terms of flops or cores or whatever you would need on board to perform the work in a real environment?
I see. So I'm showing you at least 10 different algorithms, right? I think each algorithm is different. They are in a very wide spectrum in terms of flops. The most efficient one would be the one I was showing you, pedestrian detection on a $3 chip. That's the lowest computational cost. And the highest computation cost would be, pedestrian detection system on a GPU, because that's mission critical. So we want to do it very reliably. So yeah, they have very wide spectrum in terms of computation. Yeah.
Hi, I've got a quick question. Do you anticipate in all of this assisted driving that there will be times when you're going to actually update the matrices of weights and biases? Or is that going to be completely fixed when you buy the car and, in that sense, non-adaptive?
So from manufacturer perspective, I think they probably wish to have a very robust system, deliver, that's it, without updating. But I think from user perspective, updating is beneficial because no system is 100% robust, right? So being able to update will make the user safer, especially when you change your driving pattern from winter to summer, from summer to winter. The environment, if the environment is different, it's better to make your system to be different as well. Sure. So, but how to make this kind of updating to be more reliable and trustworthy, make sure there's no other adversarial attack come along with the updating. So these are the security questions.
Yeah, besides the security, I'm always interested in, you have a lot of different systems that are interplaying, and in each one, compromises are made in the learning process, short floats and change of gradient algorithms, whatever. And I have to believe that there are unknown interactions and uncertainties when you put this all together as a big system. And my comment is that's going to be the biggest challenge for all this, is the holes.
I fully agree with you. So one of the problems I see in the research community is that oftentimes people are interested in push up the performance from 99 to 99.9 to 99.999. But no matter what, it will not be 100%. There will be some error at some point, right? But right now, most of the system is not able to predict the robustness of the system, meaning I don't know when I'm going to fail. Exactly. So that's the difficulty part. If I don't know when I'm going to fail, then whenever fail happens, I have no way to know ahead of time. I have no way to do anything about it. That's a big problem. I think I was organizing some workshop. We wish to do more research on the robustness estimation to essentially to know when I'm going to fail, when I'm going to be very fragile on certain environment. Yeah.
So here's my question, and I get that the way you measure things is frames per second real-time image processing, but when you're doing that processing, are you using one GPU per one data stream, or do you have multiple data streams on one GPU, or do you need 10 GPUs to do one data stream?
There's a different combinations, right? So typically during the inference time, it is one GPU does one or multiple tasks. That's very possible. Yeah. Or we don't use GPU, we use a CPU to do processing as well. So I think from user perspective, during the inference time, during the testing time, it's always better to use the lower cost, processing units for sure.
Totally get that.
And it's many times the algorithm cannot live with the low cost chip. That's a problem. Meaning algorithm demanding using very expensive chips. Otherwise, algorithm will not perform. Mm-hmm. That's the thing. So we need to develop better and more efficient algorithms, basically.
Okay, thank you.
I actually have a follow-up on that. So you're it looks like you're still kind of early in some of the work. Yeah. And so so you talked about GPU or CPU. In a perfect world, do you optimize with ASICs? I mean, what's a perfect technical solution to this problem that you can envision? So
oftentimes when people are trying to optimize the efficiency, usually they put efficiency as a loss function in the training stage. Meaning during the training, I'm not only trying to improve the accuracy, but I'm also trying to lower the computational cost. Mm-hmm. The computational cost can be modeled by flops. So I'm trying to minimize the flops as much as possible. In the meantime, trying to push up the accuracy as much as possible. Mm-hmm. So eventually, it will be the weighted average of two objectives. Mm-hmm. And depending on certain application, which objective is more important, you can tune or change the weights between the two objectives.
So, but based upon what you see in the market and anticipated changes in these sort of unique accelerator designs, FPGAs or ASICs, do you anticipate that there'll be something emerging that will kind of hit that ratio in a more consistent way?
I think that the battle between the accuracy and efficiency will always be there, because people are always want more, want lower cost, want high accuracy. So I think the contradiction between the two will always be there. You just have to tune your design for particular purpose or application scenarios.
Okay.
I don't see an ultimate solution for that, basically.
Yep. Thank you very much.
Yeah.
Are there any other questions? No? Dr. Liu, thank you very much.